Of course, most fires occur in larger, more complex structures than simply a 12 by 12 room. It's important to take what we now know about fire behavior and fire dynamics and apply it to the structures in which we work.
When we have fires in structures, we have a lot of interconnected compartments, but the physics of the fire remain the same. The heat rises, the hot gases expand. This expansion creates an area of higher pressure. These pressurized areas will try and equalize, looking for the path of least resistance. Because of the complexity of the structure, the flow of these gases becomes more complex.
A term used to describe this flow of gases and the volume they travel in is flow path. Flow path is the movement of gases throughout the structure. It's the flow of cool air into the fire, and then it's the heated gases from the fire exiting to a ventilation point. In the previous example, the flow path was contained within the room. We had fresh air going in low in the doorway, and then the hot gases coming out high in the doorway. So we had our inlet and our outlet. If we place that same fire deeper inside a structure, we have to be concerned about where the fire is going to get its fresh air and where it's going to be moving the hot gases of combustion. You could have a situation where you have several flow paths within a structure depending on the ventilation.
When you're conducting fire operations, you want to try and identify and control the flow path, or at least understand the flow path and adjust your tactics accordingly. Placing firefighters into a flow path between where the fire is and where the fire wants to go will place members at a significant risk due to increased flow of fire, heat, and smoke towards their position. That's why we need to train our firefighters to identify and control the flow path. When forcing a door to search, one member of the team should stay at the door to keep the door closed. That is controlling the flow path and denying air to the fire so the fire won't grow as rapidly or move towards the firefighters.
Wind is the most important consideration to fireground operations, especially in regards to fire dynamics. It's very important to keep wind at your back when fighting a fire. You don't want to get downwind.
This video will show you in real time how rapidly that fire transition occurs when the window fails. There's a 20-mile-per-hour wind pushing through the structure, and you can look at the conditions that result in the corridor. In the corridor, untenable conditions for a firefighter are generated within a period of seconds.
This wind created a flow path within the structure, in through the window, down the corridor, and out the stairwell.
The concept of using a wind control device to block the wind blowing into the fire area has shown to decrease the convected flow path downwind to a degree that would allow for safer operations for the firefighters.
A basement fire has always been a heavily ventilation-controlled situation because it's very difficult to ventilate below grade. Usually the windows to the area are very small. These are always very difficult, hot, smoky fires. Often there are interior stairs. However, if there is another entrance other than the interior stairs, that entrance is preferable.
In more modern construction, many basements have walkout doors, exit windows, much larger window vents, and now these set up a high hazard. If the firefighter is approaching from above, if one of those windows should be vented, accidentally break out, however, it would change the flow path such that fresh air is coming in low in the basement, increasing the heat release rate of the fire, and then the exhaust gases would be going up the stairs. In effect, any firefighter trying to come down the stairs is in the chimney. They're in between where the fire is and where the fire wants to go, and that's a very hazardous place to be.
Flowing water through a window was something that was very taboo years ago. But now it's acceptable to reduce the temperature in the basement, reduce the chance of a collapse, and then find a way down. Basement fires are a very dangerous situation. The firefighter's job is to break the fire tetrahedron and to put out the fire. There are three basic ways to accomplish this task: eliminate the fuel from the fire, cool the fire, or deprive the fire of oxygen. Although addressing the fuel load is a tactic when dealing with wildland fire situations, it is not usually a tactic that is appropriate for structure fires. That leaves us with cooling the fire and limiting the oxygen to the fire. When talking about limiting the oxygen, we need to look at the various tasks that we perform on the fire ground, such as search. Prior to entering a building for search, if we can limit air to the fire, we can help minimize fire growth. The main way to do that is door control. In most regards, it's nothing new. A lot of firefighters were taught that. Door control, door control, door control. You get into the apartment, close the door. If you're preparing fire attack on the front porch, close the door until you're ready to attack. Minimize the ventilation and potential flow path until you can cool the fire with water.
A common tactic around the country is vent enter search, VES, now called VEIS. We've added the I for isolate. If your department performs VES, if there's a door there, close it. You are isolating yourself from the fire, removing the potential for creating a flow path and accelerating the fire's growth. A direct attack on the burning fuel with a straight stream is the most effective way to extinguish a fire.
There are times when a direct attack can be a challenge. As the hot gases move through the structure, we may need to negotiate through that environment, through those hot gases, just to get to the fire. In the event that the environment becomes too hot and untenable, to avoid injury and even to avoid flashover, the nozzle firefighter may need to open up on the gases overhead to cool them. This is sometimes referred to as an indirect attack. This can bring the temperature down in the environment and allow the firefighter to move forward and attack the fire.
Once in the fire room, the combination attack is an effective way to attack the fire. Sweep the nozzle back and forth across the ceiling to cool the fire gases. Then drop the stream down onto the burning fuel, removing the heat and extinguishing the fire. What are the cues and clues that a company officer needs to know in order to tell the difference between a fuel-limited and a ventilation-limited fire? In this experiment that NIST conducted with the Phoenix, Arizona Fire Department, you can see initially when the fire starts that it's pretty clear that there's a fire in the structure. Then as it becomes ventilation-limited, it actually begins to look like there's not a whole lot of fire.
As the fire runs out of oxygen that it needs for combustion, it reduces the amount of heat and therefore the amount of pressure it creates. Therefore, there is less smoke being pushed out of the building.
The front doors are ventilated at the 8-minute mark, and now the fire is receiving additional oxygen. And as we would expect, the fire increases again. Finally, as it gets down into the 16 to 18-minute mark, there is a catastrophic roof collapse. So in the early stages, at the 3-minute mark, this is a fuel-limited fire. If you were to roll up on this fire, you would see some smoke being pushed from around the roofline and some smoke coming from an attic ventilator. The windows would be clear, or you would see water vapor on the surface of the windows. As fuel begins to burn, one of the things that initially gets liberated is water vapor, so you might see water vapor. But other than that, the windows would be relatively clear. Any paper signs would still be affixed to the windows. Curtains and vertical blinds would still be intact. There wouldn't be a heat signature on the walls or windows if viewed through a thermal imaging camera. There would be no evidence of smoke stain along the vent exhaust. Here we are at the 4-minute mark. If you were to roll up on this fire now, you would clearly see that this is a well-involved structure fire. There would be no question as to what's going on here. As we move ahead to the 5-minute mark, the fire is now in a ventilation-limited or ventilation-controlled state. It's used up most of the oxygen in the interior. From the exterior, we don't see a whole lot. However, arriving at the 5-minute mark versus arriving at the 3-minute mark, we are dealing with two radically different fire scenarios.
At the 3-minute mark, if you were to open the door, adding additional oxygen into the building, it wouldn't have much effect on the fire behavior. You're really fighting the fire at the incipient stage. Now, at a ventilation-controlled stage, when you open the front doors, you add the additional ingredient to get the fire back rocking and rolling, a much more dangerous situation.
What are some of the signs that tell us that the fire is in a ventilation-controlled state? Most of the time, we're not going to arrive on scene within the first 3 or 4 minutes of a fire. So when you show up, the fire is more likely to be in a ventilation-controlled state. If you were to roll up now, you wouldn't be able to see through the windows. They would be soot-stained and black, and anything on the inside of the windows would look fuzzy. Any signs or paper affixed to the interior of the windows will be burned or heat damaged. The exterior doors and windows will be warm or hot to the touch. If you have a thermal imaging camera, you'll see a residual heat signature on the doors and windows. You may see soot or smoke stains around the exhaust openings where the fire had been exhausting earlier before becoming ventilation limited. As the pressure decreases, the heat release rate decreases, and smoke is no longer being pushed out. But the soot stain from the smoke being pushed out earlier would still be visible. People may have reported a thermal column, but you don't see one while you are responding. Often people will say, there was a lot of fire here earlier, or there was a lot of smoke, but there is nothing shown when you arrive on scene. That's a good indication that the fire is now in a ventilation-limited state. Here we see the doors are ventilated at the 8-minute mark, and here at the 11-minute mark, the fire is clearly now getting more oxygen. The heat release rate is increasing, and we see the evidence of that from the exterior. Finally, at the 18-minute mark, we see the collapse of a major portion of the roof. Here is some actual fireground footage we can use to put this information to work for us at a real-world event. This was a fire from back on November 7, 2010. Some of the things that we can see here is some soot and smoke stain from where this fire had been pushing from above this doorway. We've got this characteristic smoke stain showing from the front side of the building. We can also see, when we look at these front windows, that they're dark and soot stained. It's a good indication that even though we can see some of the vinyl siding is on fire, and we can see some flame in other parts of the building, that at least in this compartment, the fire is in a ventilation-limited state.
When dealing with fire dynamics in structures, remember that fires can be in different states in different compartments in the structure. This room may be ventilation limited. However, another room in the structure may be post-flashover.
Here at the front corner, there is smoke being pushed from the attic void. But when we look down at this compartment, we can see that the windows are blackened and soot-stained. So if we go back to the front door, we know that forcing the front door is ventilation. You don't open the front door until you have a charge line in place, everybody's on air with full PPE, and you're ready to make entry. In this case, there was a delay getting the line to the front door. When that happens, the front door should be kept closed. This fire was clearly in a ventilation limited state from what we could see from the exterior. And opening the door is allowing the one ingredient the fire needs to get the heat release rate going again and increase the fire behavior. Initially, the front door is acting only as an air inlet. We don't see any smoke rolling out along the top. When that occurs, the fire usually has an exhaust vent somewhere else. That's not to say that once we've created this flow path, that we're not going to draw the fire back towards this side of the structure. Here you can see that the fire is now starting to vent out through the top of the door. They're still waiting for a line to be brought up to the front. In this case, the better tactic would be to keep that door closed to limit the amount of air that is being introduced into this compartment.
As we had mentioned earlier, we must limit the flow path in all of our tactics. If we perform VEIS, remember to isolate the room we are in by closing the door. If we have a team searching another part of the building, the closed door will control the flow path of hot gases out and fresh air in, maintaining a safer environment for that search team.
Here, we can see that that opening is turning into a bidirectional vent. Cooler air is being drawn in near the floor, and smoke is coming out through the top of the door. Now we start to see active flames as one of the windows is vented and even more air allowed in. The fire behavior is increasing and the heat release rate is going up. This compartment is transitioning to flashover. You can see here, by taking these other windows, all it is doing is allowing more air to the fire. The result here is obvious.
When applying fire dynamics to the fire ground, you have to consider all the variables possible in order to make the best decisions.
It's important to look for the telltale signs to tell you what state that the fire is in. Most of the time, the fires we roll up on will be in a ventilation-controlled state.
We have to use that information of how to adjust to attack the fire and how and when to ventilate the fire.
Remember the fire tetrahedron. The fire needs fuel, heat, and oxygen, and a chemical reaction.
Coordination of ventilation is more important than ever. Now that we understand what is going on in the building, we have an obligation to vent at the appropriate times when fire attack is in progress and not before. Of course, there will always be exceptions, and the better you understand what is going on with the fire, the better decisions you will make on the fire ground.
It is very important to locate where the fire is and identify the fire's flow path. You don't want to be on the downwind side of the fire. Keep the wind at your back. You don't want to be between where the fire is and where it wants to go. This is a high hazard location. An understanding of fire dynamics will provide you with additional tactical options so that you can increase the safety and effectiveness of your firefighters.